Okay, we're going to take section 9.6 and we're going to break it up into two parts. We're going to call this one part 1, and we're going to have a little mini quiz over just section 9.6. Almost all chemical reactions involve exchanging of energy, either loss or gain in energy. So to determine the change in energy for a reaction, we look at the energy of the reactants and products. The units we'll be using is the SI unit for energy, and that would be the joule, or more commonly the kilojoule would be the most common unit that we would use. The heat of a chemical reaction is the amount of heat absorbed or released during a reaction. It is also known as the enthalpy change. That's a new word for us, enthalpy. It just means the heat. It is the difference in energy of the reactants and the products. It's shown as the symbol delta H. Delta meaning change, the little triangle, and H meaning heat of reaction. So it's the change in heat between the products and reactants. In an exothermic reaction, heat is released. So an exothermic reaction is going to feel hot. And delta H is negative. So the delta H of a exothermic reaction is negative because the energy of the products is less than the energy of the reactants. So when I subtract, I come up with a negative number. Heat is considered a product in an exothermic reaction. So we can write that heat as part of the balanced chemical equation. So we can either write it as an additional product, or we write it separately and say delta H equals negative 185 kilojoules per mole. So you can write it either way. If I were to graph the energy of a reaction, I see here that the energy of reactants is high and the energy of the products is low. So when I subtract, I get a negative sign. And this difference is the energy that is released. So that is an exothermic reaction. So I see the heat written as a product, or I see it here written as delta H is a negative 185 kilojoules. In an endothermic reaction, heat is absorbed. In an endothermic reaction, it's going to feel cold because heat is being absorbed. The delta H of an endothermic reaction is positive because the energy of the products is greater than the energy of the reactants. So we'll end up with a positive number. Heat is considered to be a reactant because heat is going in, it's being absorbed. So we can write it with the heat as an additional reactant, or we can write it showing that delta H has a positive 181 kilojoules. Again, looking at it graphically, the energy of the reactants is low, the energy of the products is higher, and the difference between the two is the amount of energy that is absorbed. So we write that either as the heat being as a reactant, or with the delta H off to the side being a positive number. So just remembering that in an exothermic reaction, heat is released, heat is on the product side, and it has a negative sign. Delta H is a negative sign. For an endothermic reaction, heat is absorbed. We see the heat on the reactant side, and the delta H has a positive sign. So if I have here 1 mole of carbon and 1 mole of oxygen gas making carbon dioxide gas, right? The energy produced is 394 kilojoules lower than the energy of the reactants. So the first question is the reaction exothermic or endothermic? Thinking about the energy of the products is lower. That means energy had to be given off. So this reaction is exothermic. Right? Write a balanced equation for this reaction, including the heat of reaction. So we're going to say carbon, solid, reacts with oxygen, gas, to produce carbon dioxide gas. Right? So we're going to include the delta H of the reaction. And it's 394 kilojoules lower than the reactants. So that means our delta H is going to have a negative sign, 394 kilojoules. So the delta H is going to be negative. The value of our delta H refers to the kilojoules for each substance in the balanced equation. So looking at this decomposition reaction, we have water decomposing to make hydrogen gas and oxygen gas. And the delta H for this reaction, that should be delta H, sorry, is a positive 572 kilojoules. Also written set the second way here with the 572 kilojoules as a reactant. So either way, this is an endothermic reaction. Energy is going in, and 572 kilojoules are absorbed. Well, how much is absorbed for each reactant or product? Well, we talk about how much is absorbed per mole, and we use the coefficients in the balanced equation. So 572 kilojoules are absorbed by 2 moles of water to produce 2 moles of hydrogen and 1 mole of oxygen. So we can do this, write these as conversion factors for each substance in the reaction. So for example, for water, we can write 572 kilojoules over 2 moles of water, or 2 moles of water over 572 kilojoules. And we can do the same thing for the hydrogen and the oxygen. So in this, with these conversion factors, we can then use them in a calculation. It says, suppose in this reaction that 9 grams of water undergoes a reaction. So I'm going to start with 9 grams of water. Well, I can't do anything with grams, so I need moles. So the first thing I'm going to do is to divide by the molar mass to give me moles. And then because then I have moles of H2O on top, I'm going to use this first conversion factor with kilojoules on top and moles of H2O on bottom, 572 kilojoules over 2 moles of water. So 9 divided by 18.02 times 5.72 divided by 2 is a positive 143 kilojoules. You do need to include the positive sign when we're talking about heats of reaction. So how much heat in kilojoules is released when nitrogen and hydrogen react to form 50 grams of ammonia? So there's our balanced equation. Here we see our delta H is a negative number. So negative number means it's an exothermic reaction. Heat is being given off. So we know we have 50 grams of the ammonia. We're looking for the heat released in kilojoules. So we're going to need the molar mass of ammonia, and we need the enthalpy change, or delta H, of the reaction at negative 92.2 kilojoules. So here's our plan. We're going to start with grams of ammonia. We're going to use molar mass to get us to moles of ammonia. Then we're going to use the heat of reaction conversion to get us to kilojoules. So how much heat in kilojoules is released when we start with 50 grams, when we form 50 grams of ammonia? So I'm going to start with that 50 grams of ammonia. going to use molar mass. Moles of NH3 on top. Molar mass of NH3 is 17.03 grams. Then my grams of NH3 cancel, leaving me with moles of NH3. So this time I want kilojoules, so I'm going to put the kilojoules on top. I get negative 92.2 kilojoules for every 2 moles of ammonia. That 2 right here comes from the balanced chemical equation. Looking then, moles of NH3 cancel, and I get kilojoules as my final unit, which is what I was looking for. So I'm going to take the 50, I'm going to divide by 17.03, I'm going to multiply by negative 92.2, and divide by 2. And then I come up with a negative 135 kilojoules, and that would be the heat released when I form 50 grams of ammonia. So that's it for part 1. We'll have some mastering tomorrow, and then we'll move into part 2.